He will not
At the beginning of the 20th century, the mechanisms that were proposed early on weren't thought to work because there was no way to redistribute mass and angular momentum, and that was a huge problem for a century. So then they came up, Chamberlain and Moulton came up with this passing star hypothesis. You rip off a bit, and that would help you get the mass and angular momentum where you wanted to, but of course the chances for that are very, very small in the Milky Way. That was already known. So planetary systems were rare. I'm an empiricist, so I'm very sad that after World War II it took theorists to come to the rescue and propose a mechanism, turbulent diffusion, to redistribute mass and angular momentum. But anyway, Spitzer and von Weizsäcker did that and then enabled us to say, yes, maybe the process that leads to stars leads to planets too. And there we are, 50 years and a bit more. Good. This discussion has a context of life in the universe and how probable or improbable it might be. As an astronomer, I just want to put my ground rules on this conversation. Life needs energy, and because of that, it's probably a planetary phenomenon. At least that's going to be my starting point. And that, of course, is the entree for planetary systems and their formation to be important in this conversation. So Suzanne did a great job, I think, of destroying the concept of the habitable zone, which I very much appreciate because I think it's very limiting. And this is meant to be an old grainy slide because I think it's a bit of an old grainy concept for all the reasons that Suzanne mentioned. It's broader than that, and we are too proud to think that we understand it to the depths that would lead us to design space missions solely to look for planets that confine to our narrow view. That's my particular take on that subject. So the question one is always asked, and I asked it to students at all levels, do you think planetary systems like our own are common or rare in the universe? And of course it's a poorly posed question. What do you mean by like our own? And of course the answer must depend on the integral of those probability density functions over the ranges of the relevant parameter spaces for life, which I pose we're very ignorant on anyway. But we'll come back to that in a minute. Maybe there's another one out here to replace our 9th planet. We'll see. So Suzanne again introduced the demographics already. Here's what we have. If you look at some catalog of exoplanets, you'll find dozens of things called directly imaged planets. I'm a bit more circumspect about that. I have a very narrowly defined definition of something that is small around a star that I would argue could have been formed through planetary-like processes. And by my count, there are now about 11 such objects. And they're unusual by the standards of the other planets. And I'll come back to this, but this is what we need to describe from formation theory. This is one of the films I wanted to show from Matthew Bate down at Exeter, of how stars form from molecular clouds. So there's a competition between gravity and support mechanisms, internal energy support, magnetic fields, rotation, other things. And what Matthew is showing here in his simulation is how the importance of radiative feedback. So you see the massive intermediate mass stars are lighting up and having a feedback of energy into the local environment that is changing somewhat, not completely, but somewhat the star forming properties. The environment of how stars form is important in setting the initial conditions for how planets form and the early environment of their evolution. But stars form in groupings of dozens to hundreds to thousands to hundreds of thousands of stars in the most extreme. And that was a hydrodynamic simulation from Matthew's computer. This is a picture with Hubble of a young star forming region, hundreds of small stars forming near a handful of big ones. That has to do with the initial mass function of stars and how we understand stars form. But environment matters. It may not be the most important compared to the physics of the microprocesses, but environment does matter. And how might it matter? Well, there's a couple of things. Photoevaporation from the very intense energy of very bright stars in the center of a star cluster, as you saw in the past slide. Dynamics certainly can play a role, probably not a dominant one. A handful of planetary systems appear to be disturbed through dynamical interactions with their neighbors, but not all planetary systems are disturbed because our star clusters as they form are not dense enough, so we think. But a curious one you may not have heard of is the pollution of protoplanetary systems by radioactive elements that could come from massive stars, in particular supernova. And it's thought our own solar system had significant amounts of iron 60 and aluminum 26, which heat forming planetesimals, change their structure and their volatile content, because that's an important part of how planetesimal forms. It's a very important heat source in the early phases. This is a study we did of what fraction of sun-like stars in a star cluster through typical dynamics end up with the appropriate amount of aluminum 26 comparable to our own solar system. It's about 10%. So it's not 10 to the minus 5 and it's not 100%. It's a bit, but not so tiny. But these effects need to be taken into account. So the initial conditions of star formation in those clouds that Matthew was simulating, we have the interstellar medium. That's what I abbreviate here as ISM. That sets the kind of composition of the stuff that's delivered to the nebula and then is further transmuted by the chemical and dynamical processes. But we know what's in the interstellar medium, and it's a starting point. These clouds collapse through a very energetic processes, this competition between gravity and support mechanisms. And also, there's a distribution of specific angular momentum in those forming cloud cores of molecules of gas and also dust. I focus on this because it determines the multiplicity properties of forming stars, that distribution of specific angular momentum. And it also dictates the size of the circumstellar disk that forms around a forming star. And that can also be an important input parameter. What is shown here in this funny diagram is an accretion rate, an infall rate onto the protostellar system as a function of time. And our standard theory of how a single star forms through this lovely 30 years of discussion on the topic suggests that a very tiny seed forms with the material that has the smallest amount of specific angular momentum. A little disk forms around it. That disk becomes unstable, dumps its material onto the central star. The disk then can grow larger around a slightly higher protostar, and this process can repeat over and over again, maybe a couple of dozen times, until your last, and what these bumps are meant to be are these instabilities that occur many times throughout that evolution. It's the last stable circumstellar disk of order about 10% the mass of the protostar, that say is 0.9 solar masses. That's the kind of last stable disk where the planets that form in that disk will survive this final process, and those are the ones that we're going to care about as being potentially habitable planetary systems. So now some more data. I'm going to talk a little bit about the observations we have of circumstellar disks. I'm going to digress into a phenomenological discussion of the theory of planet formation and what it predicts, and then show you some of the outcomes that we have and give you some highlights for what we can expect in the future. These are models of circumstellar disks of the mass surface density of solids as a function of orbital semi-major axis that are informed by resolved observations from the millimeter wave interferometers that we have access to. So this is sort of the state of the art, but new observations from the ALMA interferometer in Chile are not included. My point in showing this slide is that yes, there's a range of orbital radii, but you're dropping by several orders of magnitude at some size scales about 50 to 200 times the mean Earth-Sun distance. So over those size scales of order 100 AU, that's the size of a typical circumstellar disk. We have elaborate, sophisticated models, and I mean that in a pejorative sense, to fit the spectral energy distributions of these objects. And we come up with very sophisticated models. Many of this is informed by what we really think is going on and assumptions about the fundamental physics, but it's the resolved observations that will really test these models hard. But nonetheless, we have some evidence already for discontinuities in the distribution of materials, both gas and dust, in these systems. We think there are inner holes in these systems at about 0.05 AU, and that may explain the stopping point for some of the hot Jupiters to where they might migrate in the inner circumstellar disk. There are also places where we think, at the ice line and so on, where planets might form efficiently, but these discontinuities, for whatever reason, represent dangers and opportunities for planet formation, as I'll talk about in just a minute. Now this is a representation of the mass of a circumstellar disk as observed in millimeter wave observations of the dust component of those disks versus the mass of the host star. And there's quite a dispersion, but there's kind of this upper limit. And again, from our theories of star and planet formation, we expect there to be such a relation. More massive stars can sustain more massive circumstellar disks without violating this gravitational instability limit that led to those bursts that I talked about before. Now, the fact that there's dispersion here means that you see evolution already from that t=0 moment, but we do believe that this upper envelope means something, and it's a starting point. So when modeling theorists ask me what to begin with, I'm optimistic. I say, start with the most stuff you can at the 10% the mass of the star, and then we'll see what your models can do with that optimism. We also have access to millimeter and mid-infrared observations of molecules in those disks, and those observations of the molecules can give us some hints as to the abundances of different molecules in those disks and how they evolve over time. These are observations from the Spitzer Space Telescope. We can't wait for new ones from the James Webb Space Telescope, which will be tremendously more powerful than these. But we already see trends in some molecular species like water, seems to be very infrequent around the intermediate mass stars of 1 to 3 solar masses. I don't think it's because those stars never had water vapor in their inner disks. I think it's because their disks evolve much more quickly. It's hard to catch them with the water vapor. But we see acetylene, C2H2, CO2, a wide variety of these molecules that are in the stuff that has the building blocks of planets within them. And so those are the things that are delivered to these planets that Susan was talking about, so that we can derive what we would expect to be their bulk composition from initial conditions like this. This is a cartoon of disk evolution, where we start off at the early times with a very massive disk. It's very highly flared because as you go out, the hydrostatic pressure in the disk decreases as you move away from the star, and so at a fixed thermal temperature it can broaden out. There's accretion onto that central star. What's also not often thought about is that as solids form in the disk, they're thought to migrate inwards, and that is a conveyor belt for bringing volatile materials, C, N, and O primarily, into the inner disk. And once they pass the ice line, they might give up those volatile materials into the gas phase. And those are discontinuities in molecular abundances that we are looking hard for right now. At some point, the disk starts to dissipate, photoevaporation, where energetic radiation from the central star releases bonds in the atoms or molecules and gives them enough extra kick that they are on escape orbits at those orbital radii. That can lead to a photoevaporative flow, lead to a hole opening in the middle of the disk. The inner disk goes onto the star, and the outer disk slowly floats away as it feeds this photoevaporative flow. That could explain a place in the planet distributions at about a few AU, where maybe there's a pileup already seen in the orbital distributions from the demographics. And then at very late times, you have debris disks. In our system, that's the Kuiper belt and the asteroid belt in our own solar system. I want to spend just a couple of minutes, this is going to take me a bit too long, to work through some very first order theory of how planets form. And again, we start with the interstellar medium, which is built of carbonaceous and silicate-rich materials. Turns out it's a bit of a mystery why the major planets in the inner solar system are carbon poor relative to silicon with respect to the sun. And that's an interesting story we can talk about in the discussion period. But I like to think of the Safronov growth time as basically the doubling time of a rock of some density and radius. And it goes as 1 over the surface density of solids and the Keplerian frequency. This basically just tells you how often something bumps into something of its own size and doubles in size. That's how things grow from microns up to millimeters or centimeters. The biggest things can have an extra impact due to gravitational focusing, so that the rich get richer. The largest ones will run away, and that depends on the local escape velocity to those big guys relative to the thermal distribution in the parent body of the small solids that are being vacuumed up by the big guys. We used to think there was an important concept called the isolation mass, where eventually you eat everything into 5 plus or minus 5 times your Hill sphere of influence in that circumstellar disk, but that ignores migration. It would just say that if you had a rock at some special place that did nothing but eat all of its small neighbors, you could grow up to this mass, and this tells you how that mass would change with various parameters. But that ignores one of the central features of planet formation, is that solids move in the disk, and that's something we now need to take strongly into account. I don't want to dwell on this, but one of the key parts of forming giant planets through the classical core accretion model used to explain our own solar system is how do you get a core of a gas giant planet that can initiate runaway gas growth. And the calculation goes something like taking the equations of stellar structure that astrophysicists have used for more than half a century, and assuming that the luminosity of a forming protoplanet is dominated by accretion of small solids in an accretion luminosity. And by using those equations and solving them self-consistently, you can derive that there's a maximum mass that can support an atmosphere before it would collapse down upon it. And that's what we call the critical mass. Now, this critical mass we often say is about 10 Earth masses, and isn't that a problem because Jupiter probably does not have a core that's that size? No, the core mass can be many things, and it depends on variables such as the opacity in the forming protoplanet and the accretion rate onto the core. So it can be as small as 3 Earth masses, it can be 10 or 20 Earth masses, it will really be whatever you want, but within this theoretical framework, it should match these criterion based on the variables that you can change. So forming cores, this is not a way to describe how cores form, it's just placing a numerical construct on what their sizes could be. Forming them is still a huge problem. Then finally, once you form a core, you will ultimately need to accrete the gas, and that's this runaway growth. So what you see here is, over time, the various mass components, the core mass in red, and the gas mass in green, and the total mass is the sum of the two. So the core saturates, the runaway growth happens. One question is what shuts off the runaway growth of the gas in core accretion? It could be that a gap forms, and maybe that limits the mass of the gas flowing onto the planet, but that's actually not thought to be true anymore. It could be that the photoevaporation of the reservoir just goes away, or it could be something funny, like the microphysics of a circumplanetary disk that is feeding material in detail onto the forming protoplanet. Maybe there are feedback mechanisms in there that we need to understand. I hope not, because things are now getting very complicated, but it's not so simple to understand what shuts off the gas. Now a bit of phenomenology. I'm not going to walk you through. This is really just algebra. I'm trying to use these little formulas introduced before for how fast things grow, and then take what I think I know about circumstellar disks and how they evolve to predict that there is an outer radius, an orbital radius, at which you would form the core of a gas giant planet. And I'm trying to show here that it doesn't depend very strongly on star mass, given what we know about the structure and evolution of circumstellar disks. It's very hard to form a core beyond tens of AU. This we know from the theory. But it's also true for M dwarfs as well as for A stars, and it does not appear to depend strongly on stellar mass, I would argue, through this phenomenology. You can also do some back-of-the-envelope calculations to work out what masses you expect as a function of primary star mass, and I would argue that you would expect the masses of the gas giants you form through this mechanism should depend linearly, more or less, on the mass of the star, and indeed, as Susan alluded to, there is some evidence to suggest that that may be borne out by the data. I haven't talked about gravitational instability, where locally a parcel of gas is unstable to its own gravitational field relative to the gravitational field in which it exists in the circumstellar disk, plus also the rotation locally that could be supporting it as well. This is the concept of gravitational instability in the Toomre Q. And again, if you play these phenomenological games on what I think I know about circumstellar disks, this depends weakly on stellar mass to the 4th power, but more strongly on radius. It's more likely to locally fragment if the disk is cold and slowly moving at large orbital radii, independent of the mass of the central star. And also you can work out what the typical fragments should be, and they ought to be of order 5 Jupiter masses. So you're looking for massive planets beyond 50 AU if you like this flavor of planet formation theory. I'm not going to talk about migration. It's very complicated, it's not well understood, and it's certainly not well understood by me, but there are problems here, and it's one of the main sources of uncertainty in predicting what we should see in the outcomes of planet formation compared to the demographics that Susan showed. So back to this diagram, which is planet mass versus orbital separation. Core accretion is wanting you to form planets inside of tens of AU. Gravitational instability is wanting you to form planets outside of 50 AU, and yet we see a handful, but still some, gas giant planets in this intermediate zone. The RV data are suggesting more planets at smaller masses and more planets as you go out, at least out to 3 AU. And we'll have to see what happens from beyond that. As Susan said, we can now use extreme adaptive optics, very high actuator density on very large telescopes, 8 meters, and soon in the future 30-meter telescopes. And we can take pictures of planets, as is shown here, in 6 different wave bands to create a spectrum, such as Susan was suggesting. We can then characterize the atmospheres and look for these molecules that could be important in understanding the objects. Now, I want to spend a few minutes and tell you what we think we've learned from observations of circumstellar disks about some of these funny processes. What you're seeing here are pictures of scattered starlight from dust in the disks, and the light is coming from the star and scattering off of dust grains into our line of sight. And we're starting with these very fancy telescopes to get beautiful images with resolutions of a few to 10 AU of just remarkable structures, like this one here, with almost looks like a grand design spiral. When we compare these scattered light images, which are tracing scattering of starlight off of small dust grains, compared to millimeter wave emission, which is basically tracing the thermal emission from larger dust grains, say a millimeter, we start to see differences, which suggest a picture that dust filtration is going on. What do I mean by that? Well, solids in a circumstellar disk will want to orbit at the Keplerian frequency. Gases, however, feel gas pressure. And provided that there's a global pressure gradient in a circumstellar disks, they're rotating sub-Keplerian. So the solids that are wanting to rotate at Keplerian velocity feel a headwind compared to the gas in which they're embedded, and that tends to make them spiral in to the central star. This is a main problem for losing solids that we want to form planets, and we have to find ways around it. At 1 astronomical unit, a 1 meter sized body like this table, more or less, would zoom into the sun in about a century, given typical parameters for these gas gradients. At 10s to 100 AU, a millimeter-sized particle, which is the one that moves the fastest, moves much more slowly. But at different orbital radii, there are different speeds for different sizes, and that creates dust separation in the disk. What's shown here is this idea that if you have a local pressure bump, this is actually a big help, because all of a sudden the pressure gradient is reversed right here. So this acts as a great attractor for all the tiny particles from here inward and from here inward. And all of a sudden you'll start collecting things like crazy in those places, and that could help you form solids much more quickly, perhaps the seeds of giant planets. Here's a cartoon, and this is actually used to explain the kinds of observations I was showing, where the millimeter wave cavities are much larger than the cavities you see in the small grains through scattered light. So there's a big hole in the inner disk, you have a collection of small grains here, and larger particles are at larger orbital separations. Here's another beautiful image. Oh, the projector doesn't quite do it justice, but if you took a power spectrum of that, there's so many frequencies that have interesting information on all scales. It's really quite remarkable. This is an intermediate mass, 2 solar mass star, a huge cavity of about 100 astronomical units. Lovely little sculpted features all throughout this disk, dozens of them detected. A little bit of shadow here. And this is the millimeter wave, where the highest concentration is right here where we see no scatterers. One idea used to explain this is that there are vortices forming. Something like a Rossby wave instability can be triggered at a very steep gradient in the surface density and trigger a local instability. The argument here is that maybe you formed a collection of planets inside that has helped carve out the gap in this disk, and that is already creating the conditions to trigger another body to form outside of it. And this would be an idea of sequential planet formation from inside out, if these ideas hold up to detailed scrutiny. This is just a qualitative suggestion at the moment. I want to move now to a couple of observations of real, what we think are real embedded protoplanets that we're just catching in the act. And here's one such example. Now, before I was showing you scattered light, this is now thermal emission at much longer wavelengths, about a factor of 5 longer wavelengths, but not millimeter. This is emission at 5 microns, so you're tracing temperatures of several hundred kelvins in thermal emission from Wien's law. And there are extended components to this thermal emission, but also compact objects. There are compact sources seen here in multiple bands, in multiple observations. And we've seen this now in a handful, 3 different systems, where we think we have data that suggests the forming presence of a protoplanet, helping to carve out these disks around young star systems. We try to get as much data as we can. In this case, we've gotten 3 data points. And the SEDs for the spectral energy distributions of these forming protoplanets look funny, and they suggest to us that we should add another emission component, like a circumplanetary disk. You would naturally expect a circumplanetary disk to be forming around a point mass in such a circumstellar disk. A gap may open, but material still moves through the disk, and it can collect around the protoplanet and perhaps feed a flow onto the planet itself. We, of course, know that the Galilean moons in our own solar system for Jupiter formed in such a circumplanetary disk, and to some extent some of the moons of Saturn. We're just at the edge now of, I think, of making real unambiguous detection of circumplanetary disks and then characterizing their properties. And this is just a simulation of what we think we could see with an ELT, 39-meter telescope, but also ALMA should be able to resolve the thermal emission from a circumplanetary disk around forming protostars. So we're very excited about that. Okay, let me spend a minute on outcomes, as Susan already went through the demographics in a way. But as a person who does direct imaging of exoplanets, one of the things we have to keep reminding ourselves is that they're stars, and many stars have companions, low-mass stars, or binary star companions. And as you move it down into the brown dwarf regime, objects that don't fuse hydrogen into helium in their cores, but essentially act in some ways, as Susan alluded to in her mass radius diagram, like planets, we expect that the companion distribution of star-like objects to be falling in this regime, and the planet masses go up to very small planets. So this is relative frequency versus the log of the planet mass, or companion mass. So this is 0.1 solar masses, 0.02 solar masses, and 1 Jupiter mass here. And if you add these two distribution functions together, in just the way that we know the frequency of companions to sun-like stars as low-mass companions, and planet frequency, you actually expect a local minima. We've seen this in radial velocity data, and we're starting to get hints that it's also true from direct imaging data at large orbital radii. And every survey should see this. And this actually will move as a function of the host star mass, and that's something that I really am excited to see, if we can see those local minima and see them change. Now, this is very speculative, and I'm really in danger of getting scooped here, but I wanted to show something interesting, at least to Suzanne or some of the other experts in the audience. Piecing together surveys of exoplanets from many different lines of attack is a very interesting thing to do. And if you put together, this is now for M dwarfs, very low mass star primaries. We have from radial velocities, this wobble of the star in response to the planet, some constraints on the gas giant frequency around M dwarfs out to 1 AU. From microlensing, and this only works for M dwarf primaries, which we think are the main host sites of microlensing planets, we have a detection of what the frequency of gas giants is around those objects, and then from direct imaging an upper limit. We'd like to posit that this distribution function isn't a power law with a strong cutoff, which is what our community has sadly been using for so long, but it's actually a log normal distribution. And there are many reasons why that would be a very natural thing for it to be, and it could well peak at 10 AU. The data are consistent with that so far. Finally, let me move on. This is about finding other Earths. So let me spend a minute talking about how other Earths form. They form through collisions of Mars-sized objects inside the inner solar system, at least. This is just a plot of the mass growth of different bodies as a function of log time. This is 10 million years here. It takes between 10 and 100 million years to take of order 10 Mars mass objects between 0.7 and 1.4 AU to bang together chaotically over time to form an Earth-like planet. And many simulations bear this out. We think that these giant impacts are important. We don't know exactly how important. This is a lovely cartoon of a Mars-massed object crashing into another one. You can imagine what's going to happen when all that kinetic energy is released. When they do smash together, oh, watch out, it's going to hit you. It's going to melt, and it's going to be very, very hot for a very short period of time. I'm particularly excited about this with the next generation of telescopes, because we can actually, if we're lucky, catch these. They're so bright, they're very easy to see, but they cool very fast unless they have thick atmospheres that thermally insulate them for millions of years. So I'm excited that maybe the next generation of telescopes we'd actually catch evidence of protoplanets like this in formation. Of course, this is a famous explanation for the Earth-Moon system. And can't see this figure here, but the predictions of how large this magma disk around the Earth was right after that event, I mean, it's several Earth radii. It would just burn a hole in your infrared detector if you see such a thing in the 10,000 years before it cooled. It would be tremendously easy to see such a thing. I want to say just a minute about compositions of forming planets. We can play parlor games from chemistry and dynamics, and if there are any geochemists in the audience, they would be familiar with the condensation sequence and what its limitations are. But given standard temperatures and pressures for a standard collection of elements like a solar abundance, we can predict what solids should condense at different places in the nebula. And many of us have done that, played this game as a function of orbital radius. Different species will largely condense out into different mineral phases, and you can predict. We then assign those mineral compositions to kilometer-sized rocks in a planetesimal distribution, and then hit go on n-body simulations, which then later agglomerate these bodies into planets. And by doing so, we can predict the bulk elemental compositions of these bodies. There are many reasons why this is a terrible thing to do, and it's shocking how well it actually reproduces the elemental abundances of the terrestrial planets. But there's a series of papers by many groups, this was ours in Zurich, playing this parlor game. It gives you some hint on how chemistry and dynamics can play together to predict the masses of planets. I'd be remiss if I didn't mention, at least in the context of this talk, the very peculiar dynamical history, we think, that obtained for our own solar system. There's a very, again, sophisticated model whereby Jupiter was migrating into the inner disk due to this type 2 migration due to viscous evolution. But Saturn, which is much smaller, was migrating much more quickly due to type 1 migration and caught up with it. And when it did, it evacuated the region between the two planets and then changed the dynamics of the migration fundamentally. The push from the inner disk onto Jupiter then was much greater than the pull or the push from the outer disk onto Saturn, which was pushing inwards. And then the migration halted and changed direction and moved outwards. Very special circumstance of Saturn catching up to Jupiter, if you will, and helping, and then the inner disk is really the pushing agent, pushing it backwards. This is very elegant to explain why Mars is in fact so small in our solar system. So the Jupiter would have moved into about 1.5 AU before it reversed course and moved outward. The gas was all there, by the way, during this time, and then ultimately the gas dissipated. Later dynamical evolution led to the Nice model, which was a dynamical rearrangement of Jupiter and Uranus and pushing them farther outward, which then disrupted the Kuiper belt. But that's a related but slightly different part of the story. But this Grand TAC model is very elegant at explaining some of the important dynamical features. But if you want to call it fine-tuning, you can. It certainly didn't happen in every solar system. That would be too much to ask. But things like it could have happened in many kinds of systems. Right, so here's a quick, 5 more minutes? Here's a quick summary of the planet formation. Much is known about initial conditions. You just have to trust me there. We have a lot of data, and good people are working on this, doing their best to constrain the initial conditions for planet formation. We're increasingly aggressive about forcing the modelers to use these constraints. So it's been a very healthy dialogue the last decade or so. We do have some understanding of the major processes, but there's a lot of gaps, and in particular migration theory is poorly enough understood. It creates a huge problem in really predicting what the emergent population should be at the end. Certainly, as Suzanne said, planet formation is common. I hope I've convinced you it's complicated, and I think that can be a good thing. And certainly the outcomes are very, very diverse, and this leads my philosophical viewpoint on fine-tuning in this context. I think the data are consistent with a very dynamically rich set of evolutions, and by that I mean many planetary systems look like they could be dynamically full. You know, if you tried to add one more planet, you couldn't. Our own solar system is dynamically stable in its configuration on the time scale at which we observe it. So it's sort of always adiabatically adjusting, if you will, to whatever current dynamical state that it's in. And also not all planetary systems are in resonance. In fact, not very many, 10, 20% of the Kepler systems that Suzanne talked about. This to me suggests that there's dissipation, but not too much. You do have damping mechanisms in this, but not everything is completely damped all the time. Finally, our own solar system does exhibit many peculiar properties, but you have to be careful about interpreting that as whether that's really weird or not, depending on what the parent distributions are of those properties, and in particular, which ones are we going to care about for habitability. Let me skip the ELTs, except to say, in addition to what Suzanne said about reflected light, there's a handful of stars where the next generation of telescopes, we can actually take thermal images of planets around the nearest 10 or 20 stars. This is not well understood, but it's possible. And if we could get spectra of these things. I would say a few of these objects, depending on good performance or not so good performance. But we might be able to get a couple of super-Earths where we could really get thermal emission spectra just from resolved imaging. I like this slide, which I stole. I don't know who exactly showed it first, because they both show it, and I couldn't get the timing right between Sean Carroll and Flake. But this idea that complexity increases, but then it decreases as your entropy is driving a system to evolve. And I think this is kind of an interesting concept in terms of planet formation, between 10 and 100 and maybe a few hundred to a billion years, there's an awful lot of complexity in the systems. At very, very late times, the complexity is rather low, even though the entropy is higher globally when you look over all the systems. And I guess I'm not so pessimistic that nature won't find some way to utilize this complexity to do what it wants in terms of creating life. So here's my final philosophic slide. I think planet formation is very complicated, and I don't even want to talk about the biochemical origins of life. That's even more complicated. I would like to remind us, when I was reading through your background material on this fine-tuning business, our theories are useful, but they're wildly incomplete. And so for me I'm not a fine-tuner, let's put it that way. I think we see what we can see, but we don't necessarily see what must be. And by that I mean, if things were a little bit different, the strong force to the electromagnetic force, yes, iron wouldn't be the highest binding energy per nucleon, but I don't know what that world would look like. But I have kind of faith in the universe, or the multiverse at least, that many, many other interesting things could happen, even if I can't imagine them in the moment. And I think I'll just end with homage to Epicurus, who already thought that everything that ever could possibly happen would happen, and that's his version of the multiverse being very resourceful. Thank you very much.